I've only just realized that there's actually a bunch of bin bags in the corner of the screen behind me. It's because I'm leaving my classroom. It's very sad. But let's go into what we're actually doing now. We're looking at gravitational potential energy, and like the kinetic energy video before, what we're going to do is we're going to examine what gravitational potential energy actually is. We're going to understand the components going behind it, so how you can make it bigger or smaller, and we're then going to look at the formula behind gravitational potential energy. So hit the like button, come and join me in the back, and we'll do some physics. So when it comes to gravitational potential energy, what we need to do is take an object, and raise it above the ground, and then that will give it some gravitational potential energy. But we need to look at the components which give it more and more gravitational potential energy. Essentially what we're doing is we're moving this away from a gravitational field center. And that means that, well, this is made of mass, and the gravitational center is made of mass, usually. So these things will attract, right? And they want to attract, so they want to be close to each other. And if you take these things apart, then you need some energy to do so, and that's gravitational potential energy. And there you go. There's a couple of factors in making this, putting numbers to this. So I'm just going to show that to you now using the medium of textbooks. So gravitational potential energy. Now this is an GCSE physics book, revision guide, CGP guide. Really good thing to get. Does not replace actual learning of things at all. This only gives you a general overview. If you really want to have nuances on physics, you're going to need to watch my videos or do some practice questions. You know what? Do the practice questions first, then watch my videos, or do both at the same time. It might actually be helpful. But basically, this is a nice thin book. And what we're going to do is we're going to demonstrate gravitational potential energy by the bang that these produce when you let them fall to the ground. Basically, if we have this object here and we drop it from a certain height, it has some energy, and when it hits the ground, that's transferred sound energy, and you get a little bit of a bang. If we were to increase the height, we get a bigger bang because the thing has dropped further. So if we get a bigger height, we get a bigger bang. Basically, there's more energy involved in this one. Now what we can do is we can increase the mass of our book. So this is your physics textbook if you're doing IGCSE or Cambridge IGCSE. And what we can do is drop it from a small height, and you can hear it makes a bigger bang than our CGP guide. And then if we raise it up above, a nice big bang. And if we raise it even higher, a nice big bang. So basically, more mass, more gravitational potential energy, more height, more gravitational potential energy. And then what we do is we take this, which is our IB diploma book from Cambridge University Press. And this is a nice thick textbook. And if we drop it from a short height, makes a nice deep sound, a lot of energy there. And if we drop it from the maximum height, then we get... So what we have for this is GPE, or gravitational potential energy, is going to be proportional to the mass of the object. It's also going to be proportional to the height at which the object is above the ground. Now I also want to remind you of this formula here, where we said energy is equal to force times distance. Now we have a distance in the height of this one. So we can say that gravitational potential energy is going to be equal to something something times by height, right? So then we have, hang on, just by height. There. We also need a force. Now, force is going to be a mass times by acceleration. That's Newton's law, right? So Newton's second law. Okay? Basically F equals ma. So F equals ma. There we go. And we've got a mass component up here. Now we want energy, and energy is here. So we have mass times by some sort of acceleration. Now, This is kind of why I don't like teaching energy before teaching forces and things, because I'm going to put something in here and it won't make sense until like a few months down the line when we look at what this stuff is. But I'm going to put a letter in here, and this is G, okay? Gravitational acceleration. Okay, basically this is the acceleration that you experience on the Earth. Now if you were to go to the moon, this number, or this constant here, would be less, which means that you end up having less gravitational potential energy, even if you had the same mass and the same height above the ground. So there's three components at play here. One, you have the mass of your object. Two, you have the height of the object above its gravitational center, or at least the difference in height it moves. And then you've also got the strength of the gravitational field which you're operating in. If you were to go to the sun and then move the same height above the ground using the same object, you would be burnt to a crisp. But you'd also have higher gravitational potential energy. So that's the idea there. It's the mass of the object times by the gravitational acceleration times by height. Now this is sometimes given to you, but if it isn't, it's going to be 9.8 meters per second squared, or just 10 meters per second squared. Depends on what the exam board's giving you. There we go. So that is actually an acceleration. We've got mass times acceleration there. And that's why we have energy is force times distance, or we can say energy is mass times acceleration times distance. So energy is mad. Energy is mass times acceleration times distance. So energy is mad. Okay. Anyway, gravitational potential energy, mass times gravitational constant times by height. And there you go.